In the previous video, we started our discussion of the important thin film processing techniques. We discussed the sputtering deposition and the evaporation deposition. We will now continue with an alternative evaporation technique often used for the deposition of cadmium telluride, namely closed-space sublimation. Like the other physical vapor deposition techniques, closed-space sublimation takes place in a vacuum chamber. Two graphite blocks are placed close together, ranging from a couple of millimeters to 1.5 centimeters, and are separated by two spaces. The substrate is placed on one of the graphite blocks, while the target material is placed on the other. Two heater lamps are used to heat up the graphite sources up to a temperature of about 500 degrees Celsius. The temperature of the graphite block is controlled using a thermocouple. The heat of the graphite block causes the target material to evaporate. The substrate is kept at a slightly lower temperature than the target. Since material tends to deposit on colder places in a vacuum system, transport of the evaporated target will occur from the bottom to the top. Variations on this technique are also used where an inert gas like argon or nitrogen is introduced in the vacuum chamber to have improved control over the deposition. This figure shows a closed-space sublimation tool. We can clearly discern the graphite blocks in the vacuum chamber. Now, the chemical bath deposition will be discussed. As the name suggests, the target material is dissolved in a liquid chemical. The bath is heated and the temperature and acidity of the solution are controlled, since they can affect the properties of the deposited film. For the actual deposition, substrates are introduced in the liquid and the target ions grow a film on the substrate. A spinner improves the homogeneity of the deposition. A chemical bath deposition is often used for the cadmium sulfide, which is an important material for the cadmium telluride and CIGS technologies. For the deposition of the 3-5 semiconductor PV technologies like gallium arsenide, a deposition technique called epitaxy is used. In epitaxy, crystalline layers are deposited on a crystalline substrate. The deposit layers adopt the crystalline lattice structure of the substrate. There are two main epitaxial deposition techniques which we will discuss here. These are molecular beam epitaxy and metal organic chemical vapor deposition, or MOCVD. This figure shows the vacuum chamber of a molecular beam epitaxy, or MBE deposition tool. A substrate is placed on a heating element, which raises the substrate temperature up to 600 degrees Celsius or even higher. The substrate and heater are attached to a rotating arm. For 3-5 technologies, the substrate is generally a monocrystalline germanium wafer. The chamber contains multiple effusion cells, each containing a separate target element with a very high purity. Each of the effusion cells is closed off with a shutter. If you want to deposit a certain material, let's say for instance intrinsic gallium arsenide, the shutters of the effusion cells containing the gallium and arsenic elements are opened. In an effusion cell, the target material is evaporated, generating an atomic beam aimed at the substrate. The term beam means that the flux of the evaporated atoms does not interact with any other particles in the chamber until it reaches the substrate. The target atoms deposit on the substrate surface where a crystalline lattice is grown monolayer by monolayer. A beam flow gauge measures the atomic fluxes at the substrate. The flux of an atomic beam is controlled by the effusion cell temperature. To prevent the incorporation of any impurities or vacancy defects in the grown material, the process takes place in an ultra-high vacuum environment where the pressure is below 10 to the -9 bars. The pressure is monitored again by an ion gauge. Furthermore, the chamber is cooled using liquid nitrogen. The cryogenic temperature of the liquid nitrogen acts as a sink for any impurities in the vacuum. To accurately measure the growth of the crystalline layers, a so-called reflection high-energy electron diffraction system, or RHEED system, is often used. As the name implies, the system shoots a focused beam of high-energy electrons towards the surface of the substrate under a shallow angle. For a small fraction of incident electrons, diffraction occurs. The diffraction patterns are observed on the fluorescent screen of the RHEED system. Since the penetration depth of the electrons is only a few monolayers deep, the diffraction pattern provides information about the growth of the crystalline material. The layer-by-layer growth process and the high substrate temperature and high vacuum conditions make molecular beam epitaxy an expensive and slow process. Therefore, typically 3-5 semiconductor layers are deposited by using metallic organic chemical vapor deposition, or MOCVD. In MOCVD, the epitaxial growth takes place through a chemical reaction rather than through the physical deposition that takes place in MBE. MOCVD does not take place at ultra-high vacuum conditions, but at moderate low pressures. This figure shows an MOCVD chamber. The substrate is placed on a heater, which raises the temperature of the substrate to between 500 and 1500 degrees Celsius, depending on the desired material. A gas flow is passed over the substrate containing the precursor gases and a carrier gas like hydrogen or nitrogen. For the deposition of gallium arsenide alloys, the precursor gases usually consist of a metallic organic molecules containing the target atom with multiple methyl groups or hydrogen atoms attached. A typical precursor gas is, for example, the 3-methyl gallium, which is shown here. The gallium atom in the center is connected to 3 methyl groups, each consisting of a carbon atom and 3 hydrogen atoms. In a similar manner, 3-methyl aluminium and 3-methyl indium are used in a precursor gas. Arsenic and phosphorus, on the other hand, are bound to 3 hydrogen atoms to produce arsine gas and phosphine gas. For the deposition of the intrinsic gallium arsenide, a flow of 3-methyl gallium arsenic gas and a carrier gas like molecular nitrogen is pumped into the chamber. In order to deposit a crystalline material, the precursor gases need to be dissociated. Thermal energy coming from the heater partially dissociates the precursor gas in the gas flow. Intact and partially dissociated gallium and arsenide particles alike diffuse to the substrate surface. The high substrate temperature causes the gas particles to further dissociate, so that the mostly pure gallium arsenide is grown. As a result, layer by layer of gallium arsenide is grown at much faster rate than molecular beam epitaxy of up to 1 nanometers per second. The remainder of the precursor gases, so the hydrogen and methyl groups, partially combine to form methane. The methane carrier gas and any other unused gases are flushed from the system. Due to the higher deposition rate and absence of an ultra-high vacuum, MOCVD is much less expensive than MBE. However, a relatively large amount of impurities like hydrogen, nitrogen, or even metal groups are incorporated during the MOCVD process. MBE therefore produces a higher quality material. Another deposition technique known as atomic layer deposition, or ALD, can take place in a similar chamber as MOCVD. We will discuss ALD and a final deposition technique in the next video.